Welcome again to the August 2018 meeting of the Association of Information Technology Professionals, North Central Florida. That's CompTIA AITP-NCFL. Our presenter tonight is Mr. Tony Barr. He will be speaking on programming in the language of thought. Tony was born in New York, educated at North Carolina State. He is the co-creator of SAS. He has several patents for two-dimensional, trim, thank you. He's designed a number of processing workstations for the IBM mainframe. He's designed the first commercial linking loader for the IBM OS 360. He's designed programs for used in production of United States and international mortality statistics and computing exact probabilities for four-deck blackjack. Without any further ado, I'd like to present Mr. Tony Barr.
Thank you, Michael. I want to just tell you a little bit about this talk. I have always been interested in understanding everything, so that's why I studied physics. And when I heard about computers, I was drawn to them. And I sometimes say I was the first programmer because there was nobody around to learn from. I was given a manual on the instruction set of the computer, and I was told to write analysis of variance program. And the two people who were working with me left about 2 weeks later, and so I was the only one. Now, this is programming somewhat theoretically, you might say. So what this was write the statements out on coding sheets, give them to the computing center, they punch them up, we get a listing, and I single step through that listing. So I did that for 6 months, and the computer finally came in. And when I put the program into the computer, I was confused about what the printout said. I asked somebody who had programmed the calculating machine, and he said, these are flags. They didn't have error messages. They had an F for format, a U for undefined, an M for multiple defined. So just a little letter, that was your hint. But anyway, the reason I bring this up is because I think I'm in the same situation now, because I am inventing a new programming paradigm, and I have to imagine that I am inside that programming paradigm to write the programs and to prove that it would be successful. So now, the theme of this talk is programming in the language of thought. I have that title because of several things. People used to say to me, well, what are you going to do with the model reality? That's what I named my company, and that's what I'm developing. And so I had to do something. I said, well, don't you have a model reality? And everybody said, oh, and it ended the question. So now this was always a joke to me. But since I am doing this model reality to be like a global model, you could call it the global brain. It's analogous to what we have in our mind. So it's that putting these things together. Now, I'm first going to give you two paradoxes that I was struck by. Back in 1980, I read this book, Data and Reality, by William Kent. And he had 3 pages in there where he said, the schema is always separate from the objects. That's a lot of pages for, a 250-page book. And it always rested me, well, this is always true, the schema is separate from the data, but anyway. Well, I went off to a course by this guy, Bertrand Meyer. And Bertrand Meyer wrote the book Object-Oriented Program Construction. And he's the co-inventor of the Eiffel language and very well esteemed in computer science. The ETH is in Zurich. And the first day I'm there, in the morning, he's sort of fluff he's talking about. So he's prancing up and down the front of us, and he says, he shows us an Eiffel program. And he says, look at that program. There are no objects in it. There are only types. You got to run the program to produce the objects. So another manifestation of this paradox. So this always struck me. Now, I will get to you to solve this paradox, I think, in this speech. But I am fascinated by this relationship Wang had with Kurt Gödel. After Einstein died, Kurt Gödel got to be best buddies with Wang. And Wang was a mathematician and a computer scientist. He came to this country in 1946, went to MIT, pretty much stayed there. But he tells what was on Gödel's mind. One of the things that I found fascinating was Gödel, you could say, didn't believe in his Gödel's theorem. Now, that's kind of a silly statement, but Gödel's theorem was that no system can be consistent and complete. That's the way, everybody says it, but what he meant, or even in the title of his paper, was no system. I mean, it was that essentially why Principia Mathematica would never work, or similarly defined systems would never work. What he was talking about, if you use syntax to define your system of logic, you're always going to get ambiguity, syntactical ambiguity. So I have a system that doesn't use syntax, so that's maybe it could be consistent and complete. Now, in that same book, there is a little reference that Gödel said that if you took the word in mathematics, you start off with set theory and define what a set is. He said if you change the word set to concept of a concept, you could define all of logic. Now, Gödel was a logician and a mathematician. I'm not a logician at all. But now this had a very nice ring to me, because I had been using the term type of type for the initial thing. A type of type would define itself, would define all other types, and a type would define an object. But that was a peculiar type of type, never rang very well to me. And then if you use concept of concept, well, we have all these concepts in our mind. It rings from a human standpoint. And anyway, it's a self-defining thing. Now, actually, the way that it's self-defining, at least the way I have done it, is a very simple thought, is that when you talk about object-oriented, you normally talk about methods being in the type and variables being in the object. I use a slightly different language. I talk about connections. And the connection is either a uniform connection that is the same for all objects of a concept, and then you have the variable connections, which are different. Anyway, I'm just saying I'm a compulsive guy about self-definition. And you look at the Bible, it's got I am that I am, the ultimate self-defining statement. You know, Moses asked God at the burning bush. That was his answer. And you've got this statue of self-definition down in Winter Park and by Pulaski. And this was essentially symbolic of his life, how he created his own life here in this country. Now, self-definition is what we live with all the time because every cell in our body potentially could define a new cell, right? So it's self-defining. And Shakespeare said, "To thine own self be true." Now, it seems to me this is a pretty good test. Is the system consistent enough that it can talk about itself and be consistent with itself? Here is a example, sort of a recursive example of who's pulling whose string. Always there's a bigger puppet master pulling the little puppet string. I use recursion to define the whole system, but I use little pictures which are just boxes, and sometimes if they got parameters, there's boxes inside of boxes. But let's say we've got program X that has no arguments, and so you can that in my system that's a command, and a computer can execute a command. Well, this is using computer. You know, if you executed computer on program, it would interpret the program. Now, since computer is nothing more than a bunch of instructions, you can have computer interpreting the program. And this is just for grins. You could go on forever with this thought. So you can define very precisely the system in terms of itself using this system, this mechanism. Now, the programming language is a high-level language, so you're interpreting it within a high-level language. Well, this was a fun day. This was the Christmas party at the biostatistics department over at University of Florida. And I was invited there, and I sat with the former head of clinical sciences at FSU. And I threw out this term, concept of a concept. And he started telling me all about concept maps. And he started drawing concept maps. Apparently this was the way he taught his students. It was just, I thought, was an incredible thing. Well, I came away from that thinking, well, I'm going to change my language from type to concept. It's certainly, you connect with people. And anyway, this is a concept map. And it's actually, it might have even been drawn by the concept map program. There is a group out of Pensacola, the Institute of Human Machine Cognition. They actually have a branch in Ocala as well. But they are the keeper of the concept map software. And I actually think that mind maps look a little bit more colorful. These are hand-drawn mind maps. It's the same thought. It's concepts connected to other concepts. And here's a sort of grandiose one. Well, I put concept and connection into Google, and I got 100 books from Amazon. It's the way academics describe the world. It's the way we talk about knowledge is concept and connection. So biology, concepts and connections, physics, concepts and connections. It's just the way we describe the world. So that's a better language than type and object. Now we look at the brain. It's all full of concepts. And we look at the nerves. We got 10 to the 10th neurons. Each neuron has 7,000 connections to other neurons. It is, if you think of a neuron as being a concept, it's concept and connection. Now, the language, concept and connection, has been established in the world of philosophy by Frege, and actually Girdle was a follower of the Frege model of philosophy. And you could think of, this is just repeating that concept is a connection, and connections correspond to the synapses. Well, this is a very teeny picture of a concept. Every concept has got a parent, it's got children. That's the inheritance model. You inherit from your parent connections and you add to it new connections. And then you've got the superior concepts and the concepts that are within yourself. And derived from the concept connection, you've got the variable connection and the uniform connection. I think this is a better language than what's used in object-oriented programming with methods. It's more symmetric. Now, one thing I think when you study programming, and you study how a program works, they somewhat gloss over what an object is. And they talk about instantiating an object. The essence is every object is really made of two pieces. It's the concept. All this uniform information is factored out over here. And for each one of the objects, you got the variables. So I think it's more realistic that we talk about programming using the way it's implemented. So this, I just put the concept of a person, the name, a list of symbols, birth, date, sex, male or female. Uniforms is just an expression that returns years based upon the birth date. I just threw this in here, how you would see objects, John, Sue, and Albert, with their birth date, sex, and age. I threw this thing in because it's just kind of fascinating to me. Friedrich Heydrich is the, got his Nobel Prize for libertarian economics. And that is that the ultimate, he says price carries so much information, and that's all you really need to be thinking about. And you make better decisions if price is used at every level in the economic system. Well, he left economics in '91 and went into psychology. And he came up with a model of how the brain worked, which is similar to the way economics works. With values and neurons being rewarded for making the right decision. So he has been rediscovered. Apparently, he published back in '46, but it wasn't until like '84 or something that people, or '94, I guess, that they discovered that Hayek really had a good thing going back there in '46. Well, here's just the first place I think that artificial intelligence hit pay dirt was in pattern recognition. And here I'm just showing the top line is 4 concepts of little curved lines and straight lines. Then you got down below how these are put together. The lower level returns the primitive shape. The next level returns the letter. The third level puts it all together into dog. Now, I was fascinated to read about AlphaGo, which is the Google DeepMind acquisition. And AlphaGo, when it went after the Go game, it didn't know anything. It had to learn how the board looked, how the pieces were moved, and then it gradually built up, how to win. and it actually wins consistently over human players now. I found it interesting that the way they did this is they started at the low level, just looking at the pixels on the screen. They didn't have a binary representation of the board. They just went from the pixels of the screen, and anyway, learned the screen and learned the moves, and then learned how to win. Now, a very famous philosopher of the 1900s was Ludwig Wittgenstein. He said a picture is a model reality. He wrote a whole book on that. He said we think in terms of pictures. Well, we have a very successful computer language called Scratch that 12-year-olds just thrive on. And millions and millions, I guess probably 5 million now. When I last read it, were 4 million kids who learned how to program this. And the ACM had an article that said we need to learn how to transition the kids to syntax and semantics like the big kids program. And I actually think, why don't we change the environment so everybody programs with pictures instead of just the kids? Anyway, we need a new model of computing. And why not directly edit the model instead of bypassing the whole idea of syntax? The idea I have is that you have this mass of objects that you do organize in terms of lists, that you edit them directly. You know, when you use the Microsoft 3-tier model, the bottom is the data model, then there's the business rule model, and then there's the presentation. Well, at least the bottom two levels could be done in this and more environment. And you could do it all with pictures. And the other thought I have is that having it as a global model, if you've got permission, you could go in and read other people's models. So you wouldn't have all this converting data from one representation to another. Well, here's my pictures. This is from before when I was still using the word type. But you can see that type and object look very much the same. You know, if you looked at C program, the type is almost unreadable, except if you've got a lot of education. I believe that we could make an environment where we can essentially program with forms. I guess Aristotle said we think in terms of forms. That was his object-oriented world. Forms and objects was his terminology. Well, you see total cost here's got a value of 0. Now that you can look at that as being the end result. But what way would you define assignment? Well, I think you ought to just have a picture the way you want it. And that's the assignment statement. So you don't have to use an equal sign. You can just put a picture the way you want it. So here's logic is an enumeration, false and true. So we can see test, you can have the value false or true. And temperature, it's done by stating that it's a list of numbers with one decimal place. So here's an actual programming example. We've got details, and we want to compute dollars and cents. So on the right is a program. Now the magenta means that it's a block. It's like the do end. Now, let me say there's another part of doing this with pictures. You can see the magenta as being the outside picture. So you should be able to right-click anywhere it's magenta and pull up a description of it. So now that you could do that for sense, that's a different concept. You ought to be able to pull that up. You go to modulo, or the multiplication, be able to pull up the description of that. Now, the two points here is that you can always see the little pictures with inside the bigger pictures. With syntax, this is somewhat difficult. You have to get very highly trained to do that. We're using color. I mean, this is kind of a silly thought, but you know, it used to be that we used a camera which was just black and white. Then we got color. Movies went from black and white to color. TV went from black and white to color. I remember the green screen that came out. Didn't last but 2 years, and we all went to color. So people really find it comfortable to live in a world of color. Well, anyway, we've got this program here, and we see the magenta is a block, so it has 2 instructions inside it. The first is an assignment to sense, and that's the multiplication of modulo total cost 1. That would be give the fraction times 100 assigned to cents. So that would be the 76 cents. Down below, we're going to have to take that 76 cents off, but we have to get it back into dollars. So that's cents over 100, subtracting from total cost assigned to dollars. And on the bottom left, we have the result. And in the bottom right, we see what it would look like with code. Now with code, you've got to learn about parentheses. You've got to learn about operator precedence. You have to be somewhat sensitive to putting those semicolons at the end of the line. They teach you in Programming 101 that you need to indent the program to make it readable. So there's all these baggage that you have to carry along when you learn how to program. Now, I have a construct I call a Cartesian, because Cartesian coordinates are x and y, or x, y, and z. So this is a parallel to that. If you have discrete variables or connections, that you can use them in a sort of tabular function. I gave a talk about a year ago, and I thought, well, it toughens you up when you go out and give a talk. So I came home and thought, well, the guys only asked one good question about namespaces, which was a pretty good question. What other question? If I was a student, what questions would I ask? And I thought of this one good question. Well, have you looked at UML, Unified Modeling Language? Because they're talking about modeling. So I went and looked up UML, and it was amazing. They have a big thing on decision tables, exactly the same thing as I'm doing here. But they actually, it was a much more convoluted thing. You used one program to input the decision tables to output code and whatever. In this case, you would just use it with your editor. I call the editor the navigator. But I think that you can see the semantics pretty clearly of here, and we've defined the and or functions. Now here is it being used in practice. So the first logical unit here is the and of, if you're a teenager and your grade point average is a B or better. And that's ORed with, if you got a great SAT, or you're special. If it's true, you go to college. If it's false, you stay in the 12th grade. So this would be how you would take these pictures and make bigger constructs. And this is how do you get rid of parentheses? Well, it turns out parentheses are only used for a small set of cases. And that is when you have binary functions that are commutative. A plus B is equal to B plus A. So that's commutative. And then there's the associative, is that doesn't make any difference what order you do the process. You can work from the right to left or left to right. So if you have those two conditions, you can do the operation on a list. So that's how I get rid of parentheses. It's just define and or and addition, multiplication over a list. And just at the bottom here is just kind of a cute example where you're adding two numbers and subtracting the discount off. And I think that reads fairly well. Now, I am compulsive about defining things. Actually, you can tell how much we define things in our company. We had an enterprise model where we defined everything down to how to restock the bathrooms and the kitchens. Oh, we had the lexicon in too. That was sort of an afterthought, but we defined all the terms, everything, and we were ISO 9000. The auditor said, "Well, Mr. Barr, I've got an observation, but don't worry, it's a good observation." And he said he'd never seen anybody do anything like we had done. We had everything defined. In the language, everything's done by decomposing expressions into littler expressions and getting down and finally evaluating down to the very tiniest detail. And you finally get down to where you want to move an object from here in memory to here in memory. And here I was just using this example. It's 128 bits long. And we're moving it from the from address to the to address. We got the 4i over 1 to 128. We move from one address in the machine to another, increment the from address, increment the to address. Obviously, you would never want to interpret the language down to this level, but it's just a pedagogical idea that you would define everything down to the very last bit. In my day, when you took computer science, you had to learn machine language because they wanted to show you how the computer worked. Well, this would be a way of showing how the computer worked down to the bit level, how everything's represented as by bits, how bits are moved around. Well, I'm not going to do this because it's going to take some time, but you can jump over, since it's the Amore machine, you can jump over into the Love machine, which is kind of a cute little thing back from my day, I guess. This was just showing how there's actually two different ways that one would look at the program. The one way is by the what objects are inside other objects. The other way is by inheritance. This was just the inheritance thing. Now, we live in a world of Tower of Babel, I think, in the computers. Unbelievable number of languages there all the time. New languages being developed, and languages for this little special case, this little special case. It's my belief that we need to put all the pieces back together again. I found this fascinating. You get the Baha'i faith who believe in the unity of knowledge. And that's my goal, is to unify knowledge. So I just appreciate their feeling. They feel about the unity of science and religion as well, the unity of mankind. So anyway, the goal is to put everything back together. Now, right in the concept of a concept, there's a uniform connection to the list of people, the list of companies, the list of educational institutions, and the list of governments. And this is sort of like the .gov, the .com, and the .edu. So the thought is that you could actually deal with every entity in a uniform way. And we'd be able to walk inside the computer and look around. And backing on that first paradox, that since the system is constructed with itself, when you're inside the computer, you would see things the same way you saw things outside the computer. The guy who wrote the movie Tron was a systems programmer, and he was probably very used to going through memory dumps and being able to identify this object and this object and this object. Most people can't do that, right? Anyway, this is my logo, a model of reality. I say, I thought up the name of model of reality, and God gave me AMOR, so I'm going to use it. That's 1776 in binary. So we want to map everything into binary. And I hope in the next 3 or 4 months to actually start working on getting this reduced to code or reduced to binary. Okay, finally, no government money has been used in this research. Thank you. Anybody have any questions?
Right.
So I heard from talking to you at first that you were originally a physics major,
That's right. Mm-hmm.
and then you studied computer science.
No, but by getting the book from the bookstore, I mean, I studied it.
Okay, all right. How do you think that background in physics helped you towards, okay, you learned some programming here. Oh, well, let me conceptualize. Oh, I think I'm going to come up with the programming language SAS. And, well, that wasn't your initial thought, but that's where it ended up. And now more time evolves. Well, let me do a much higher construct, this a model of reality. So what is the evolution and the foundations of that progression of thought?
Well, I think in physics, it's a discipline where you reduce everything down to the very bottom, primitive ideas and work up. And it's a formal world. So I think that I've got the benefit of those ideas. Now, I went into physics because I wanted to be an inventor and make things. So I thought I would have a good background. But once I got into computers, it was so much more exciting because you could think it and build it. So now, just to say, I was the original founder of SAS in terms of I wrote all the original programs. And I did, up until the time I left, I did the language. So when I did the language, I was always thinking of the user, trying to make things as simple as I can for the simple case and only make things more complicated for the more complicated cases. And I did, I think it was somewhat of a feat, having a comprehensive way of handling missing data, which missing data is just life. So if the program could always have some default behavior that would be pretty much what you wanted, that meant that people could put the job in, they get the result out, and they'd be happy with the result, even though they might have had a square root of a -1 or something or other. It would treat that as a missing, and that would drop it from the analysis automatically. So just go back on physics. I have seen other people who made big accomplishments in the world of computers having a physics background as well. I think people are drawn to it for its formality and because they think they're going to learn everything, how the world works.
If you wouldn't mind
Sure.
a follow-up question on that.
Right.
So is there too much made nowadays? I want to be a programmer. I want to be a computer scientist. I'm going to study IT. And, you know, if everybody just followed this model, maybe we wouldn't be coming up with the brilliant progressions that you've had. So is there a case to be made for, before you study IT, have another discipline as a foundation?
I do think you have to have a more worldly picture, obviously, to know where you fit into the world. There's room for all different levels of people in the IT world. That's what I would think.
So I'm going to paraphrase what I've heard tonight, and I may get it completely wrong, and you've got plenty of things you can throw at me if I do. The assertion is that the different ways that we currently use to express the concept, whether they're the order of processing in mathematics or the the agreed upon specifications of a programming language like Python, these can all be removed in we don't have to agree on them. They're arbitrary, and we could actually just break it down to the core concepts to where the order of processing isn't as important, or the tabs or the semicolons at the end of a line don't matter. We could actually break it down into a language that's concept oriented. Have I got it correct, I guess is what I'm asking.
I'll answer this a little bit obscurely. Back when I left SAS, I spent a lot of money trying to build a machine to cut lumber. Decided I needed to do something that was just use my brain. So I worked on, I tried to think what would be the ultimate computer language. Well, anyway, what I finally settled on was a linguistic framework that was the grammar of grammar, that grammar of grammars define grammars, grammars define objects in a language, and it would be a completely self-defining thing. And at the same time, I read an article by Tim Teitelbaum about the Cornell program synthesizer, something like that. And what it was a syntax-oriented editor. I think he perhaps created the whole concept. But he said that he thought it was all crazy, us editing characters. He said that the programs, the language has got an underlying structure. We should be thinking in terms of the underlying structure of the program. So I think that's the big lesson, is that we ought to think of these programs as structures and ought to be conceptualizing them in our mind that way. Whereas I think we get lost right now. We don't think that way, really, when we're programming.
On that, how does this become mainstream? How is it instantiated? How does it, kind of take over the world and become, the way that we teach people, and you start with the coding and maybe learn another language later on if you have a specialized need.
Well, I talked to a senior professor about a week ago. I thought I'll just reach out and see what he thought of my idea. And he always went back to syntax. I can't write that out. I can't write that on a piece of paper. I said, well, everybody's is pretty much locked into a computer. I don't think you need to have the piece of paper. So anyway, he was sure. I mean, this guy's a very talented guy. He was sure that he would never have any need for it, and most people wouldn't have any need for it. Well, I can go back to last summer. I was having a discussion with a friend of mine, and he told me that SAS had a screw up about 7 years ago. They started charging academics for SAS. And so the academics started using the R language. And then SAS found, well, the students got their PhD, graduating, and then they start teaching their students R. So he said it's somewhat of a disaster, and SAS now gives it away again. Well, I slept on that. And I thought, well, we got these millions of kids learning how to do Scratch. That's an entry point that you could introduce a new technology. And maybe you'd get these kids being fantastic programmers. And if it's only 6 years from 12 to 18 when they go off to college, if you had it where it could do the basic spreadsheet type stuff, so they could do their homework with it, then they'd graduate from college using it, and then maybe then you'd be ready that you could actually build little enterprises with it. You could certainly run the running club's list of members and whatever, and you could get doing enterprise models on a certain scale. So then eventually you could build up to bigger and bigger enterprises. The ultimate thing that I think will make an idea such as this work is we all want understanding in the world. So if you're the president of a company and you see your competitors, everybody in that company knows what's going on inside the computer, you'd say, I want a system where everybody can understand, where we don't have to have such a front-end investment in getting people where they can understand. So I think understanding will eventually bring people to this point of view. So I think after 20 years, maybe you could really make a dent. So it wouldn't happen overnight, but that's my crystal ball.
I had a question, which is,
Sure.
you mentioned you've been working on this for a while, and you anticipate, trying to release it out to the world. Where are you at with a more? Is it still a personal project, or have you been working with other developers?
I'll just give you some history. I had my one little aborted experiment so many years ago. After 3 years on it, I said, this is not a product. I need to make money. I went off to Chattanooga, Tennessee, gave a talk, and put it on the shelf. Probably about 6 years ago, I had a woman in my office who was working on it. She was getting her PhD in computer science. And then abruptly, she left because she had a disagreement with the department. So I went a different direction, and I actually was trying to make it my enterprise model a product. But anyway, I dropped that. So I went back, essentially April of this last year, this year, I sold my property, and I've been working on the design full time. Well, actually, I had another time I had a man working for me who was a pretty competent guy, but he quit on me as well. Now, I always think that this is sort of like Christopher Columbus taking off to the west, looking for the Spice Islands. And it turned out even Christopher Columbus had a mutiny. I never realize that, because I looked up, I thought it was such an interesting thing. He had the people that couldn't get off the ship, right? But it turned out they did mutiny, and he had to go over to the one ship and ask him to give him just 4 more days, and then they saw signs of civilization after 4 days. But what I've done is I got my 25-page polished document that explains exactly where I'm going. And I've given to a bunch of people. Now, the interesting thing about it is that I hardly get any feedback, yay or nay, from it, because it's too much written like a physics article. So I have that main document that exactly explains the path. Then I have all these little documents that explain, how computer works, what the instructions are, what the semantics of them are. So I am still going to polish that, and I'm looking for somebody right now. Actually, I found one guy who had a physics major getting his PhD in computer science that I'm interested in. So that resonates with me.
We have any other questions? All right, let's give a round of applause to Mr. Tony Barr.
Thank you.
Thank you, Tony, for that very interesting and thought-provoking presentation. It's given me a lot to think about. Our next presentation will be September 25th, Tuesday again. The election process, the floor is still open for nominations. We're going to get an official note out to the membership in the short term. And other than that, I believe we are done for this evening. Thank you for watching, and we'll see you next time.
Thank you.